And dear professors and students, good afternoon.
Good afternoon.
So my name is Xiangming Lu. I'm a physics professor at the National Taiwan Normal University. So I'm going to chair this afternoon tournament. First of all, I would like to introduce today's jury. The first one is Professor Xiao Jiawei, okay, from Xie Zhongxue. So welcome. The second one is Professor Zhen Xiande from Donghua Daxue. And the third one is Professor Hong Yingguang, Shida Wuli. And the fourth one is Professor Xie Hanping from Zhongyingyuan Yuanfensuo. And the final one is Professor Jiang Peixun, Shida Wuli. And the captain, so introduce your team member's name and their grade.
Good afternoon, professors and fellow competitors. We are Team Miracle from Jianguo High School. I'm the captain, Wu Zhengwei. This is Zhang Yachen, Ye Zonghan, Chen Yanbing, and Yang Yaoan. Thank you.
So welcome to Miracle, okay, from Jianguo Zhongxue. And the opponent is the team captain. Introduce your team members.
Alright, everyone. I'm the captain of Team Mount Curie. I'm Liu Hongwei, and this is Zhuan Jun, Huang Jinhong, Huang Yunhan, Ge Shen. Thank you very much.
Okay, welcome the Curie team from Tainan Yizhong.
Yes.
Okay. The reviewers and the team captain.
Hello, we are Team Light Team from Shida Wuli, and I'm Wu Yuan, Chen Yanzhen, Wu Guoyu, Liao Senrong, Chen Yifan. Thank you.
Okay, thank you very much. So we already said the problem of the reporter is problem number 12. So Wilberforce pendulum. Okay. So you have 5 minutes for presentation. So each team write down your representative name on the blackboard.题目都选好了。啊？不是，你们报好题目。不是，你们报告。你报第二题。第二题。
上面是那个主观单位，因为跟主观单位
我打错了，没有这个，
没有那本上面打是错的。
哦，OK，
然后已经更正过了。
OK， 所以有留意我就对了。
对，
我第一场给他们的，他们名单上有错。
跟我们手册上是不相符的，我们晓得。好，谢谢冯老师。所以你们都每一场都会问我。
每一场都是第一场。
奇怪，到底是刘一伟没有？
有更正的时候，他是刘宏，印刷来不及更正。
刘宏伟，哦，那念宏啊。
是，谢谢。
刘宏伟，好。Okay, so the reporter will give a presentation.
Alright, good afternoon again, professors and fellow competitors. I'm the reporter from Team Miracle reporting problem number 12, Wilberforce pendulum. So let's first look at the problem statement. The introduction. A Wilberforce pendulum consists of a mass hanging from a vertically oriented helical spring. The mass can both move up and down on the string and rotate about its vertical axis. Investigate the behavior of such a pendulum and how it depends on the relevant parameters. So the reporter believes that there are some key questions to this problem. So first, we want to answer what is the relationship between the two motions, namely the vertical motion and the rotational motion. And next, how does one motion couple to each other, which the vertical motion eventually couples to the rotational motion and vice versa. And finally, are there other observable motions that is also interesting to be discussed? So here is our outline. So today we'll first walk through our experience and observation, where we have observed two coupled motion and also 3 coupled motions. And here, next on we'll have our dynamical analysis on first the 2 coupled motions. We will including the motions and the frequencies. And next we'll give our theory about the ideal case and have the numerical solutions, a discussion on the numerical solutions. And next we have a discussion on the 3rd motion, which is the coupling of the conical pendulum and swinging frequency. And finally to our conclusion. So first, this is our setup. So the experiment is conducted with a spring and a mass with a rod. And as we can see, because it's a 3-dimensional motion, we put 2 cameras at 240 fps from 2 directions to capture the entire motion. And because the mass down there is moving in a very it's moving dramatically, so we have to ensure the top part of the string does not move. So here we screw 2 screws on it to fix it. So here is the observation. So first we define it as a 2 motion. As you can see, there are only vertical and rotational motions. And next, 3 motions. If the initial release height has a slight deviation from the vertical axis, as you can see here, we can observe also a conical pendulum motion. Namely that the motion not only swings up and down and rotates, it also springs back and forth, as you can see. So I want to mention that there are 2 kinds of initial conditions that could start up the motion. First is we give it an initial height and release from an initial height. As you can see, the motion couples from the initial height and transfers to a rotational motion. And next, we can also give it an initial angle displacement and does not give it an initial height. And as you can see, the rotational motion also couples back to the initial height as we expected. So here is the dynamical analysis. First, we give out our terminologies. So L is the total length of the string, and M is the mass of the rod and the cylinder. And note that here we have considered the spring constant and the torsion constant. So we get our way to measure the torsion constant. First, we put our string on a horizontal plane and have a load in the end of the string. This load gives an additional torque to this string, and because the string has a torsion force, and it will reach equilibrium. And in this way, we can calculate the kappa constant from Hooke's law. So here we can see the two motions. First, okay, so there are some points I want to point out. So first, this is the the motion of the vertical motion, as you can see, and this is the motion of the rotational motion. So first, we want to see that you can see that these two motions are in phase, meaning that if one motion gets to the minimum, the other motion gets to the maximum, which meaning that the energy is transferring between these two motions. And next, you can see that there is a very apparent energy decay in their contour. And what we want to see next is the frequencies. As you can see, we put a fast Fourier transform to this diagram, and you can see that there are two main frequencies, which is the frequency of the of one motion and the frequency of a normal for the other motion. So here, we want to discuss other properties of the motion. So we separate these two motions, and we can see first. As you can see, these two motions is quite different. As you can see in the length motion, when it reaches its minimum, it also has a somewhat big amplitude. So it means that it only transfers little energy to the rotation. But as opposing, the rotational motion transfers most energy to translational motion, as you can see here. But one thing to mention, if you look closely, as time goes up, you can see that the node here is getting bigger and bigger. This means that the the energy transfer efficiency is decreasing as time goes up. So next to our theory. So first, because what the force like is difficult to know, so we choose to have a Lagrange formulation. So first is our kinetic motion. Kinetic motion, kinetic energy can be separated by the kinetic energy in the vertical direction and kinetic energy in the rotational direction. As you can see, we also consider the effective mass and the moment of inertia of our string. And next, for the potential energy, we can see that here this is the potential energy of the vertical motion, and this is the potential energy of the rotational motion. And here also we add a coupled term, and we'll later explain why we have to add a coupled term. So plugging into the Euler-Lagrange equation, we have and adding a generalized force, which is the damping force, we can obtain our equations of motions. And for our numerical solution, we use epsilon, which is the coupling coefficient, to be 0.026. So next, we want to explain the coupling term. So we can consider a string as a long wire being turned, and the total length can be calculated as an inclined thing. So L is the total length, and this little l is the total length of this wire. And by this equation, we can calculate the total length. So because the deformation, the lengthening of the string and the rotation of the string is both contributes to the deformation of the wire. So now what we want to do is that we calculate the total deformation of the wire and express this with the two apparent parameters. So we have taken the total differential of the length of the wire, and we can obtain this. So we first assume that the potential energy are stored because of the deformation of the wire and has the same form of the form of the potential energy is proportional to the square of the deformation. So here, expanding the term, you can first see that this is the vertical energy, where delta L stands for the length change of the string. And next is the rotational energy, as you can see, is delta N. And finally, the coupling energy, because the two squared and the times together. So next is our discussion. So first, when in our solution, there is a case that the natural frequencies of the two motions are coincide. And as you can see, the energy can be completely converted between each other. But in most cases, the natural frequencies are not coincide. So the energy will not be completely converted between one another. And the coupling effect of the two motions become less observable, as you can see, and both in our theory and in our experimental data. So here we want to have a comparison with the experiment. So as you can see, in our numerical solutions, the length, the components of the length also transfers only little energy back. But in the rotational, it transfers most energy back. And as you can see, it has a similar behavior. As time goes up, the energy transfer efficiency drops. So now we want to have a discussion on the third motion. So here, let's just first see the third motion again. So as you can see, it has a vertical motion, a rotational motion, and a swinging motion. So this graph is a slightly different from the previous graph. As you can see, first we can see that there is a phase lag. As you can see, the rotational motion reaches a maximum here, but for the vertical motion it reaches a minimum here. So we're asking why is there a phase lag? So because there are now three kinds of energy. First, the rotational energy, the vertical energy, and the swinging energy. So the two phases need not be together because the energy can be transferring between the three, not the two. So if one goes to maximum, the two need not to be minimum at the same time. And next, if you see closer, in the previous contour, the length of the length of the string has only two frequencies. As you look closer, you can see that the contour of the length also has a small frequency here. So why does this contour of the packet changes periodically? So this implies there's another motion which is coupled into the vertical motion. So we want to check that. So first, this is the motion of the valve. So it swings back and forth, as we can see, and we calculated the average period, which is 0.796. And next, to analyze the frequencies, we go back to the previous motion and have a first Fourier transform. And you can see, instead of two main peaks, we can see that there are other peaks, such as this. But we want to know which peak is reported, if it's a noise or a characteristic frequency. So because it's a fast Fourier transform, if we lengthen the duration of our experiment, we can have a clear analysis, and we can see that only this frequency still remains. And this frequency is approximately 0.77, and it is very close to the swinging frequency. So this means that the three frequencies are actually coupled together. So finally, to conclusion. First, what is the relationship between the two motions? So as I said, in most cases, the natural frequency will not coincide. So the energy of the two motions will partially transfer between each other. And in our theory, we have considered a coupled and damping curve, and which can qualitatively demonstrate the two motions. And how does one motion couple to the other? So in our theory, we have considered deformation of the string wire and obtained the coupled term. As you can see, we can expand the total deformation and get the three kinds of energy. So are there other observable motions? The answer is yes. If the release point is not aligned with the z-axis, we can see a conical pendulum motion. So this conical pendulum frequency can also be found in the frequencies of the length and the length motion, and that's all.
Okay, thank you. So now the opponent asks the question for the reporter.
Right, so green two.
Oh, okay. Greetings to the juries and the reporter and the reviewer. This is Team Moncrief opposing, and first I would like to ask about the you mentioned. Could you turn to the page where you are calculating the total energy? Yes, that back. Here, could you explain why the 1/3? Why does the 1/3 in front of I?
Oh, okay. So this I can show.
Please briefly explain that because this is short.
Okay, so this is considering the string of mass. The velocity of the string is not the same. It is proportional to the length. So if we have an integral on the total kinetic energy, we can have an exact mass of the 1/3.
Okay, I see. Thank you. So did you have then a theoretical explanation of the drop of the efficiency, energy transfer efficiency? You said that the energy transfer efficiency would decrease over time.
Yes.
Did you have a theoretical explanation?
Well, I don't have quite an intuitive explanation, but this shows both in our theoretical calculations and our numerical solutions.
Or did you have at least a qualitative explanation to that? Okay. No?
No, I don't have an intuitive explanation for that.
Okay. Oh, yeah, thank you. And yes, did you mention that when there are three motions,
Yes.
when one is at the maximum and the other two have to be at the minimum at the same time? Did I miss it?
Oh yes. So the phase lag is because when in the previous motion, when one reaches to a maximum, another one must reach to a minimum, right?
Yes.
Yes. But if there are three motions, the energy does not need to be like that because the decrease of one energy can be separated into two energies, so it need not to be in phase at the same time.
Okay, thank you. So now it's the preparation of the opponent. Okay, opponent take the floor.
Alright, greetings to the reporter, reviewer, and the juries. This is Team Mount Curie opposing Wilberforce pendulum. So this is the problem statement, and we're just not reading over it. Alright, so let's just go to the brief review. So first is the observation section. The reporter mentioned the problem statement and the observation video. And the pros are that they provided clear key points and they introduced the motions of the phenomenon well. And they even introduced the third type of the motion of the Wilberforce pendulum, which is really interesting. However, the introduction to the phenomenon is too less, and the observation video is not clear. Especially the video talking about a third type of the conic pendulum is not clear. So yes. And the next section, the theory, and they provided a theoretical model, the coupling term, and the Lagrange equation. And the pros are that it fits the problem statement and also the theoretical prediction. Provided a theoretical prediction, and they explain the physical meanings of the equation. However, the theories are not that detailed, and their explanations are not detailed enough, so it's a little confusing. And the next part, the setup. The setup including the capsule. Anyway, sorry, we made some mistake. Anyway, the setup including the spring and the pendulum, the Wilbur, the stick they use with moment of inertia. Anyway, so the setup, they include their setup, and the pros are that they provide a clear explanation, and the device is easy to use and not too fancy. The experiment including this is also some mistakes, sorry. And their experiments are really hardworking, and the variables they choose are important, and moreover, they also discuss the interesting third type of motion, which we think is created. However, the cons, the reporter didn't lack the expression and the explanation about their results, and they didn't have an error analysis. And finally, the conclusion, they included the relationship between the two motions, and the pros are that they clearly show what they have done, and however, they didn't well combine their experiment to a theory. Alright, so overall report, they had a special idea to the problem statement, which again is the third type of the motion, and it is very innovative. And secondly, they used Lagrange to calculate the motion, which is a really efficient, effective tool. But we're going to discuss about the cons about this method later in the discussion too. And the third, they explain their chart properly. This is another advantage. However, the weakness, the initiate of the experiment might cause error. And secondly, the lack of explanation and combination between the theory and experiment. Alright. So later, our discussion will be split into two sections. The first part is about the theory, and basically it's about Lagrangian and some are about the third type of the oscillation, and the experiment is basically about the setup and something like that. Alright, so now, Chair, I would like to go to the next section.
Okay, so move to the discussion part.
Discussion, alright. So let's start from the theory part. So I would like to ask the reporter, do you think that using Lagrangian in this phenomenon, is it appropriate or not?
Well, I would like to state that if you have studied Lagrangian, and you would know that the Newton's laws and Lagrangian equations are basically equivalent. So why I use Lagrangian is because that the forces of the spring and the vertical forces and the rotational forces, and also a couple of forces, is very difficult to know the form of the forces.
I see. That Lagrangian is an easier method.
Yes. You always can know. You can guess its energy.
But did you know about the limitations of the Lagrangian method?
Will you please elaborate?
Well, for example, to use the Lagrangian equation, you better make sure that your system is with complete restrictions. So, for example, there better not be something like damping, or you shouldn't explain.
Well, non-conservative force can be also added into the Lagrange equation. As I said, I add a generalized force, which is the damping force. Yes.
Because I don't understand that much about the Lagrangian, but according to my understanding, that the fixing to the Lagrangian, if you have the damping terms, it would be much more difficult.
Well, it's actually.
If you could provide a proof or a reference of the way you fix the Lagrangian, I think it would be better.
Okay, so by adding a non-conservative force, the first main thing you do is to add a generalized force, which is supposed here, and we have the generalized force in this form.
Alright.
Yes.
So I sorry, because I'm not so familiar with the Lagrangian, so I leave this question to the reviewer and the jury. So we expect further discussion, and there are still a lot of questions. We're going to the next section. Next, could you explain why the spring still rotate if you only give a stretch toward longitudinal?
Okay. So may we come to the backbone, please?
Okay.
Okay. So first we know that because a string is a metallic wire, it is very hard, and to lengthen it is basically is very hard to strengthen it. I mean that the total length of the string. Yes. So we can say that the total length of the string L is a conserved quantity.
Yes.
And so we can represent this as like this. So this is the length of this here, and this is the there are n turns and the radiuses are correct.
Oh, okay.
Yes. And the thing that is when this increases, because this has to be conserved,
Yes.
and when you lengthen it, the turns will not increase. Correct.
Okay.
So this radius should decrease.
I
So
agree with you.
so if you lengthen it, the radius of it decreases. The spring one tends to take it back to its original radius, so it will turn.
Okay.
Yes.
It means like something like torsion or something.
Yes, it is. It will tend to make it back to the
I agree
original
with you.
radius.
I agree with you. So the next section, did you know you have observed the phenomena of beats, right?
Yes.
And how did you calculate the beat frequency?
Well, okay, so for this, that's okay.
Use a blackboard.
Yeah. So here is the frequency, correct? You have seen that there are two main frequencies here.
Yes.
So the brief frequency, if it is a perfect addition of two cosine waves, the brief frequencies is basically the addition and the addition and subtraction of these two frequencies. Yes.
Yes.
So this is the way to calculate the brief frequency.
Okay, I have here the answer I want here. Thank you. Alright, so the next question I have asked you already in the short questions. Did you have a theoretical explanation about the swinging energy? Did you have a theory for swinging energy? Because your theory model, I remember it only includes the rotation.
Okay, so if you want to include the third energy, basically what you do is to add the two. So first, in two motion cases, the only translational energy is in the z direction. Correct. So if you add the two axes, the x-axis and y-axis, the energy, you can add the third motion, the kinetic energy of the third motion in. But I did not do this in our.
Well, and still to my curiosity, I just want to ask, if you calculate the maximum energy of each type of energy, the vertical and the rotational and the swinging,
Yes.
Is the swinging energy neglectable, do you think?
Well, I think it's definitely not.
It's definitely not. But comparing to the vertical and rotational, still think it's not neglectable?
Yes.
Okay, I guess. Alright. I see. Now next is the experiment section. Did you change, in your experiment, did you change different weights or mass and different moment of inertia?
No, I didn't change.
You didn't change that. Do you think that would greatly, do you think that's an important parameter?
Well, I think what it changes is the natural frequencies of the
Natural frequency.
the natural frequencies of the and according to our theory, different natural frequencies causes a different efficient of the coupling. So when natural frequencies are the same, the couple is perfect, as you can see. And if they are not the same, there will be some drawbacks of the.
Alright, so
yes.
I'm already here. You say that if it affects these two terms,
Yes.
the natural frequency. Alright, I see. So, sorry, because the time is limited, so some of questions have to be skipped.
Yes, that's
Because I'm more interested in the third type of motion. So, first, you introduced that you named the third type of motion. You named it a conical motion. But
Yes.
I didn't see the motion like this. It is more like this. So why are you calling it a conical pendulum?
Well, I'm thinking that what you say of the conical pendulum is the pendulum which only rotates in like this.
Yes.
So, but my definition of the conical pendulum is that it swings back and forth, and the angle of its swing can turn. So I think it's just a definition of conical pendulum.
Anyway, I'm just curious about why you named that way. That's not the that's just the naming part. So not really important. So next question. Do you think that discussing this motion is really necessary according to your problem statement? Although it's really interesting, I agree with that. But do you think that fits the problem statement? The problem statement said.
Well, I think that I have fulfilled what the problem statement has said at first, and because it is in my experiment, I observed this like interesting phenomenon, and I would like to also like.
I mean that is like something like additional research, and you think that you have already finished what the problem statement tells you.
Well, I think yes. I think I would like to add another more physical into it.
I'm not sure if this is what the TYPB requires, but anyway, that's an interesting research, and I really appreciate your work. Thank you. And all right, so now I would like to ask about the questions. And could you turn to the page that no. All right, page 11. Could you turn to page 11? All right. So it seems this is not that clear one. All right. So I will just say it. So I realized that in your graph that the frequency of the beat seems to decrease over a long time. Did you observe? I mean that the width of this beat, the frequency of the beat seems to decrease. Did you know? Did you realize this phenomenon, and did you know the reason?
Well, first of all, I do realize there is a changing of the frequency. You're saying that the frequency decrease. Yes, I have observed it, but I don't have a intuitive explanation of why this happens.
But qualitative, you don't have an intuitive.
Yeah, I don't have an intuitive physical meaning of what this.
Do you think that makes sense, or do you think that is error?
Well, I think that is not error. I think that is not error, because this also occurred in my numerical solutions.
It is the result of the numerical solution.
Yeah, I think yes.
So if we want to observe this phenomenon, what parameters should we change to observe this phenomenon to make it more significant?
Well, are saying the decreasing of the frequency?
Yeah, how to make this phenomenon more significant if we want to discuss this phenomenon.
Well, so my hypothesis is that I think it maybe have a relationship between the coupling term and also the natural frequency of the two, but I don't quite have a clear explanation of how this actually affected.
Okay, that's okay. Thank you. Right. So the next question is about definition. So could you explain the meaning of epsilon?
Well,
is it coupling spring constant or something?
Well, it is a couple constant. Depends on the geometry of the string, but I don't have a physical expression for that actually.
Okay.
Yes.
I think my time is up. Thank you.
Opponent summarized the discussion.
All right. So in our discussion, we basically split into three parts actually. So the first part is about the theory, and I discussed with the reporter about the Lagrangian, but due to my weak understanding of Lagrangian, we didn't have the conclusion for this part. And secondly, we discussed a little bit about the pros and cons of his experiments. And finally, we discussed the part that I'm more interested in is the third motion, a third type of motion. And I discussed with the reporter about the reason, about the energy of the third motion, and also we discussed about the necessity to discuss this third motion. And also, we also discussed about the reason why the frequency of beats increases as the time goes. So I appreciate that the reporter did interesting, innovative research about the third type of motion.
Okay, thank you.
Yes, thank you.
A reviewer asked the question to the reporter.
So this is the question for the reporter.
Yes.
So it seems that you use omega z equal to omega theta in your theory, right?
No, I did not have that. That is, I'm just discussing a special case, not
so
in the entire
it seems
theory.
that you can control the inertia and the mass to let these two are equal to each other.
Well,
so
it is.
do you have experiment to show that is your?
No, I don't have such.
Then another question is for both of you. Just so when the spring, when the stuff go up and down, and it will still rotate. When it rotates, the spring constant will change. Do you agree with it?
Change?
I believe it will.
Yeah, but
I don't know reason.
okay, then you believe it will change, but you use this as a constant. How do you explain that?
Well, because I believe it will change, but I don't know first how it changes, and I don't know how large it changes. So I still consider it as a constant in my theory.
Okay, then can you there's another question. Just how does the energy translate from that two motion into the swing motion?
So so you're saying like how like the forces acting.
Yeah.
Well, I think a part of it is about the pivot. So because when it's swing, the pivot is not on a straight line. So I think that the pivot can exert some forces and make to have energy transfer between the two motions.
Then do you agree that correlative force will cause this problem?
I think that is not considerably. I think that is considerably small, and I don't think that will affect this at all.
Thank you for both of you.
Okay, thank you. So the preparation of the reviewer. Okay, the reviewer takes the floor.
So there's like the team reporting. So well, I would like to go over the problem statement again.
Okay.
So it says that a rubber force pendulum consists of a mass hanging from a vertical orbital helicopter. The mass can both move up and down on the spring and rotate about a spherical axis. Investigate the behavior and such a pendulum and how it depends on the relevant parameters. So I think the group report had well prepared for the different parameters, but still they have some little tiny filter to explain the certain phenomenon to explain how their theory mesh. And they did do moving up and down and the rotating phenomenon. So I think they did a good job on it. So there are some pros and cons. So they well understanding the problem, and even they add the third motion, and they have an easy understanding graph and consider energy effectively. And there are some cons that there are no completely experiment related to theory, and doesn't talk about the deep frequency. And some of it is that they don't talk completely about how the pointing motion coupled with the other motion like the energy change or something like that, and they didn't vary his experiments. And for the opponents, they are a clear summary for the recording presentation and talk more about the theory. They talk about Lagrange, so this is something we're going to talk about later. And there are some they don't really understand how the Lagrange does the thing. So let's go to the first question. Can the Lagrange be used in this statement? So we are agree with the reporter because that they are on conservation force. They can still fix the Lagrange into the theory. So I think it's a really great part and to simplify the question. And another question is that the isolated frequency will decrease by time, and reporter says that they don't know why the frequency will decrease. So for us, we are assuming that maybe the spring constants will infect the stuff, like when they're rotating or something like that. So this is our report review.
So it's concluding remarks of the reporter.
Okay, so for my concluding remarks first, reporter believes that the use of the Lagrange equations of the theory can be properly used and can predict the motion. And next, we believe that we agree that what the reviewer has proposed, that the kappa constant and the k constant would eventually changes when it stretches or when it turns. But I think it is so for reporter, we have not constructed such experiments to verify it, and we do not have a very good confidence of how it would affect the motion. So we still consider it as a constant. And next, we have actually look at how our theory differs from our experiment. As you can see, although that they look alike, but you can see that there are still some parts that cannot match, because some of coefficients such as the coupling coefficient is actually very difficult to measure and does not know how to measure it. So we just choose a coefficient that matches our experiment data most, and that's all.
Thank you. So the questions of the jury. Be careful. Professor Hong Yuan
for the Lagrange is fluid.
Lagrange.
So I want to understand what's the meaning of C.
Sorry?
What's C?
Of this?
Which angle the first? C, yeah, this one.
Z.
How to define the C?
Definition of the Z.
Oh, it's because we didn't consider the energy of the gravitational potential energy. So the Z is the point where it reaches its it starts from the point where it reaches its equilibrium with the gravitational energy. And so here is Z equals 0.
Okay, then about the potential energy. Kc squared, what's the meaning of this C?
And this?
Yes.
Oh, it's the same Z.
C squared is the theory of the natural rate, not the equilibrium rate.
I mean that the Z, the kz squared is if is here and the Z is the length here, because we did not consider the gravitational potential energy, so we have combined it in
the potential energy is just the length displaced. If you consider C as Kc squared, you should add the n here.
I'm sorry, I don't quite.
C is a string horizontally.
Yes.
When you hang it up, it stretches.
Yeah.
But it stretches by amount. So this is not not the potential energy. The potential energy will be increased to C. That means the C, you should have a clear design of what does mean C means in this equation.
Okay.
Also about the equation of motion.
Motion.
You have data, B and data.
Yes.
You say you get the numerical solutions. How do you fix B and data?
Oh yes. It's I said it's the same as how do we get our exponent? We just choose
Choose.
Yes.
How do you compare? How do you know that it's the same as in
Well, I cannot show that it's the same as the same page.
So you just got the qualitative, not
Yes,
quantitative.
it's only,
but
but yes, the theory is just for quantitative confirmation.
So I just want a question for three of you.
Yes.
Just about a string horizontally hanging and a vertically hanging. What's the difference? And what is the similarity? Just three of you.
I want to make sure your question is that what is the difference between a horizontal spring and a vertical spring?
Yes.
The gravity is involved in the horizontal spring, and the horizontal it is not so good.
What affects motion?
What?
What affects the motion? Does it affect the motion?
What affects the motion?
Will it affect the motion?
I think if you're discussing that if the horizontal spring is fixed in the horizontal direction, then the gravity wouldn't. But if it is like you just make the spring put horizontally initially, then I think it would just swing down. And I mean, do you mean that horizontal spring is fixed in the horizontal direction and the thing is moving this way?
Oh, so what I can explain is the only difference is that if the string is placed horizontal, it will not have a gravitational force on a string. But if you put the string in a vertical, you can see that string stretches a little bit because the mass of the string itself. And I think that it will not largely affect the motion.
So I agree with the first part of this, but I think it will impact the periodic motion. Yeah.
Will affect or
Well.
Well.
Okay.
Thank you.
That's
Basic
about it.
physics. Any other questions? Okay, thank you. So now it's the grading for the jury. Are the jury ready? Ready? Okay, so the score for the reporter 7, 7, 7, 8, 6, 8. This is 6. 6, 8, okay. Okay. The score for the opponent 7, 7, 6, 8, 7, 7. Okay, it's correct. Okay. The score for the reviewer. 6, 6, 6, 7, 7, 7. Okay. Okay, thank you very much. So we close this the first round and we take a 10-minute break. Thank you. a reporter give a presentation.
Greetings to juries, opponent, and viewer. Now I'm going to report number 9, light whiskers. This is an outline, introduction and observation, theory, setup, experiment, and conclusion. First of all, the introduction and observation. This is the problem statement. When a laser beam enters a soap film at a small angle, a rapidly changing pattern of thin, branching light tracks may appear inside the film. Explain and investigate this phenomenon. And the key points are: what is the mechanism of the branching light tracks, and under what conditions will the branching light tracks happen? These are the observation videos. And the green laser beam is the incident light, and the soap film is inside the wire. You can see that the branches are formed and changes rapidly when the incident light propagates through the soap film. Next, the theory. Soap film is composed of 2 layers of surfactants and 1 layer of water. And this report defines the thickness of soap film as the thickness of water layer. And the thickness changes randomly and smoothly. In this graph, we can see that a thicker soap film will have larger refractive index, and we can also see that when the thickness is changing in a small value interval, the variation of refractive index is larger, just as the yellow part. So now we know different thickness causes different refractive index and thus cause the light deflection. So now we can assume if the range of the changes of soap film thickness is larger, or soap film thickness is changing in a small value interval, it may be easier to observe the branched flow phenomenon. Another concept must known is the correlation length. In the view of large scales, if the variations in thickness between position A and B are independent, the distance between A and B is called correlation length. Branching light tracks appear only when correlation length is larger than the wavelength of incident light. Another phenomenon that may be observed is caustics. Caustics happen when light incident through a mirror-like medium. Refraction and reflection first happens, and then diffuse reflection on a surface, and then the observer will see dark and bright areas. In the case of the soap film, the light first propagates through the curved and even interface, and here the refraction happens, and then the reflection happens on the surface of the second medium. And the observer will see dark area if the light is dispersed, bright area if the light is gathered. Next, I want to introduce the experiment setup. The camera in the soap film is fixed by the tripod, and the laser beam is placed here. And then this is the shooting of convex soap film. If we want to have heated soap film, we'll put the soap film on the heating plate. Next, this is the shooting of thin film interference. The soap film is under the artificial daylight and lamp housing. Next, I want to introduce the experiment. This is the experiment layout. In the first experiment, we have different concentrations and shapes of soap film. After measuring the thickness of soap film, we measure the branching width, the maximum branching angle of the light track itself, and we also display the photos of branched light tracks. In the second experiment, we have different temperature of soap film. We also measure the branch width, the maximum branching angle, and we display the photos of branched light tracks. In the third experiment, we have different wavelengths of incident light. So in the first experiment, is the different concentrations and shapes of soap film. We have 5 different concentrations of water, detergent, and glycerin, and 2 different shapes, flat soap film and convex soap film. And the convex soap film is divided into 3 parts, top, middle, and bottom. And then we measured the branching width, the maximum branching angle by the software image shape. We also measured the thickness of soap film by thin film interference. And the convex soap film is divided into 8 parts to measure the thickness. And then we used the software image to measure the RGB value, Python package, ColorPy to calculate the thickness of soap film. In order to display the variations of thickness more clearly, we use color map to visualize the changes of thickness. So for the first concentration, we measure the width, the angle, and the thickness of soap film. So for the flat soap film, we can see some large angles, but the numbers of branches are smaller. And for the convex soap film, from top to bottom, the branching angle and the number of branches increases. For the second concentration, these are the measured data. And for the flat soap film, we can see both large angle branches and straight branches. And for the convex soap film, from top to bottom, we cannot see obvious difference. For third concentration, these are also the measured data. And we can see that for the flat soap film, the branch angles are large and the variation of the angles are large too. And for the convex soap film, the number of branches and the branching angle is larger for the middle part, and we can also see the bright area caused by acoustics for the bottom part. For the fourth concentration, these are the measured data. And for the flat soap film, we can see more straight branches rather than large angle branches. And for the convex soap film, from top to bottom, we can see some large angles, more large angles. And for the fifth concentration, these are also the measured data. And for the flat soap film, we can see more branches, and the branches are longer, straighter, and wider. And for the convex soap film, from top to bottom, the branching angle increases. So for the flat soap film, we can see that thickness increases when concentration decreases. And when the soap film thickness increases, we found that the branching width increases because there will be more branches and there will be larger branching width. And we also found the maximum branching angle decreases. So now we can recall the graph from the theory. And we can know that if the thickness is changing in a large value interval, the variation of refractive index is smaller. So the branching width angle decreases. And for the convex soap film, we can see that the thickness increases from top to bottom because of gravity. And there are larger changes on the bottom part of the soap film. And we found that the branching width increases from top to bottom. This is maybe because it is thicker on the bottom, so there will be more branches, and then there will be larger branching width. We also found the branching angle increases from top to bottom, and this is maybe because there are larger thickness variation on the bottom, so there will be larger variation of refractive index and causes larger branching angle. We also found a special curve deflection on the convex soap film. This is mainly because the air inside and outside the soap film, and the film will move faster, so there will be large and quick changes of thickness. After continued deflecting in small distance, the curve deflection will appear. But we think this is not branched light. In the second experiment, we have different temperatures of soap film. We put the convex soap film on the heating plate and turned the temperature to 50, 100, and 150 degrees Celsius. And then we also measure the branching width, the maximum branching angle by the software image J. For the first temperature, 25 degrees Celsius, we can see that the branching width, maximum branching angle, and the number of branches increases at the middle and bottom parts. We can also see some curve deflection here. And for the second temperature, 50 degrees Celsius, we can see that the branching angle, and the curve deflection are larger and more in the top parts. And we can also see the bright area caused by acoustics. For a third temperature, 100 degrees Celsius, we still can see the curve deflection and the bright area caused by acoustics, but it is obviously not that clear compared with the previous one. And for the fourth temperature, 150 degrees Celsius, the branch light is hard to form. First, I want to explain the reason why branch light is hard to form at high temperature. This is mainly because there will be larger perturbation velocity at a higher temperature, and the thickness of soap film is uniform, so the refractive index variation will be smaller, so branch light is hard to form. And for the top part, if the temperature is higher, there will be more curve deflection, and thus causes larger branching angle. But if the temperature is too high, the branch light is hard to form too. And for the middle and bottom part, because it is near to the heating plate, so the temperature is higher, branch light will be harder to form. So there will be smaller branching angle and smaller branching width. And for the third experiment, we have different wavelengths. Here we have the red laser beam and green laser beam. But we found that the branch light track is hard to form if the incident light is red light. This is mainly because the wavelength for red light is larger, so it will be harder to let the correlation length be larger than the wavelength of incident light. Another discussion is the conditions to let acoustics appear. The first condition is at the middle and the bottom part of the convex soap film. This is mainly because the larger thickness variation here will cause a clear, dark, and bright area. Another condition is the top part of heated soap film. This is mainly because the film moves faster, so it will be easier to form the uneven surface. So at last, I want to introduce the conclusion. So for the fast soap film, when the concentration decreases, the thickness increases, and the branching width increases, maximum branching angle decreases. And for the convex soap film, from top to bottom, the thickness increases, the branching width increases, and the branching angle increases. And for the heated soap film, the thickness for the upper part is smaller, and the branching width is larger, branching angle is larger too. And for the wavelength, if the wavelength is too large, the branching light track is hard to form. And we also found two special conditions of the soap film. The first one is the curve deflection caused by the large variation in small distance. And the second one is the bright area caused by caustics. And so we will see some dark and bright areas, and it will be different from other branching photons. This is the end of my presentation. Thank you for listening.
Thank you. Now the opponent asks the question to the reporter.
Okay, first off, do you have any quantitative theory to back up your experiments? Do you have any quantitative theory?
There's no quantitative theory for the branch light itself, but there are quantitative theory for the thin film experiments.
Okay, so I also want to talk, did you consider about the polarization of the light in your experiments? Okay, and also, just a quick question. I want to know, like, how exactly did you make the soap film? What ingredients did you use to make the soap film? I want to be sure.
We add water, detergent, and glycerin.
Okay, and also I want to talk about, you talked about measuring the angle, the largest angle. Did you measure that? Where in your presentation did you measure the maximum angle for different temperatures and different concentrations?
Yes.
Can you show me where? Okay. Okay, and also I would like to ask how the wavelengths, did you only try red light and green light? Did you never tried to shorten the wavelength?
Yes, because I can only find these two.
Okay. And I also want to talk about the setup of the soap film. You said that you used a wire to contain the soap film, right? Do you think that the wire might have any effect on your experiment? The wire containing the soap film. Do you think that?
For example, can you give an example of how to affect the experiments? Because my wire is smoothly. I don't know what's.
Yeah, I'm just asking. The wire there. It's that's for the flap.
Okay, so we have to go to next to the preparation of the opponent. opponent takes the floor.
Okay, so honorable judges and fellow competitors, today I will be the opponent for light whiskers. And first off, let me reiterate the problem statement again. When a laser beam enters a soap film at a small angle, a rapidly changing pattern of thin branching light tracks may appear inside the film. Explain and investigate this phenomenon. So from our understanding, since we need to investigate and explain the phenomenon, we think that we all need to explain first off why the light tracks form and why they rapidly change. And also we want to know what the small angle is that will cause this light to appear. And so first off, let me summarize what the reporter just said. So this is the structure of the reporter. So first off, they had an introduction and their observation, and their observation was very clear. We could see the light whiskers in their experimentations. And then they had their theory. Although they didn't have a quantitative theory, they had a qualitative theory where they tried to explain how the different refractive indexes might have caused the light whiskers inside the soap film. And they also used the latch to further talk about how different thicknesses in which they would model their experiment, and also about the temperature, which might affect the velocity of the moving fluid of the soap film. So then they moved on to their experiment. We think that they did a really, really good job with their experiment because they considered a lot of different parameters, such as the shape of the soap film. They did the soap film at a flat surface, and they also did a convex soap film, so which we thought was very good of them. And also they measured different concentrations, so we could see how the concentration of the soap film also affected the light whiskers. And they also used different temperatures. And we'll get into that later because I want to discuss different temperatures. And also they measured soap films with different wavelengths of incident light. However, with different wavelengths of incident light, they only changed the parameters 2 times, each one with green light, and the second time with red light. So we don't think that they changed the parameters enough to really tell how different wavelengths could have impacted the light whiskers, because they didn't really observe the phenomenon when they used red light. And finally, they had data analysis, which of how soap film thicknesses decreased during the concentration increase. And in their conclusion, they explained their experimental data again and said that it fit with their theory of how the refractive index was supposed to work. So here are some pros and cons for the opponent. So I think for the reporter, she explained her theory very well for why there would be the light index. And all of their experiments were done properly, and like all the data was presented very well, and it was very clear, the graphs were clear. However, we think one of the main cons is that they didn't have any quantitative theory to back up their experimental data. They didn't analyze with numbers. There is no formula for them to predict how the light would branch or the angle of branching, so they do not have any quantitative theory, which we think is rather important. And also, they do not talk about the rapid changing of the light whiskers, which is mentioned in the problem statement. They only talked about how they observed different angles in the light whiskers, but they didn't talk about the rapid changing of the light whiskers. And so, moving on, these are the points that I would like to discuss. So I would like to also hear more of the reporter about their theory, and how some medium can cause the reflection, and why the refraction index changes with the thickness of the soap film, because I don't think I really understood that part of her presentation in the first part. And also I would like to discuss the experiment. So first off, with the soap film, how did the setup get to the temperatures of 150 degrees, and how they measured the thickness of the soap film. Okay.
Okay, now let's go to the discussion part.
So first off, I would just like to talk about the usage of your soap film. So you said that in your soap film you use water and glycose and things such as that, right? So I wanted to understand how in the experimental setup did you let your soap film withstand temperatures of 150 degrees?
150 degrees is just the temperature of the heating plate, but it's difficult to let the glass plate and the film itself be to 150 degrees Celsius.
So what you're saying is that during your experiment, what you meant by varying the temperature, you only vary the temperature of the heating plate,
Yes,
and not actually the soap film.
Because we are just doing a quantitative experiment, so we just want to have a cooler and hotter temperatures.
But however, since the soap film is already, for example, the soap film is at one set of temperature and you put it on the heating plate, then the heating plate is transferring heat into the soap film, right? So for hotter degrees, I understand that they might transfer heat faster, but I don't think that from this you can say that one experiment, the soap film is definitely at a higher temperature than the other.
Actually, we make the convex soap film by blowing the bubble in the glass plate.
So you blew hotter air inside?
The water or the detergent,
Yes.
the mixed is heated up to 150 degrees Celsius. But
Oh.
of course, it would not be 150 degrees.
Yes,
It would
okay.
not be.
Uh-huh. Yes,
So
okay.
I think the soap film will be.
Yes. Thank you for that wonderful explanation. So that cleared a lot of things up for me because I was really confused on how you got a soap bubble to 150 degrees. So maybe that was my misunderstanding for your report. And also, the second thing is that the soap films, in order for them to be at like the wavelengths of light, you mentioned that it should be at somewhere about 1 or 2 times the wavelengths of light in order for this to happen. But since it's so small, how did you actually measure the thickness of the soap film?
So, like I mentioned in my report, I measure the thickness of soap film. First, I just shoot the soap film under the light, and
Yes.
we'll get the thin film interference photos, and
Yes.
then we use the software imaging to measure the RGB values.
Do you have any actual images of the RBGs? Do you have any images where you actually show where you took the photos here on the presentation? Oh no, I mean the actual RBG photo where you analyze with your Python color package. Do you actually have an image of that? Like the photo you took of, so you
I don't have an image.
oh you don't have the image of that. But then so can you describe therefore then, for example, if you had a different image, so from my understanding it would have from different densities, it would have different colors, right? So how did you analyze that photo? Like what was the program you said you used Python, like how exactly did the program analyze that particular photo?
So by using thin film interference, but this is the theory for thin film interference, but
Yes.
but it's only the two lights of these two lights
Yes.
have interference, but
Yes.
actually it may be a lot of lights here.
Yes.
There
Yes.
will be interference here.
Yes.
So I don't really deeply know the theory behind the Python
yes.
but I know it is using the Fresnel equations to calculate the RGB value to the thickness.
So I agree that if the photo you take, it definitely it uses the theory of thin film interference. However, you're saying that you don't actually understand how the programming works behind the programming works to analyze you didn't write the program yourself.
Yes, I didn't write the program.
Do you think that the accuracy of the program is reliable for your
I think the
for your
code
experiment?
package is reliable.
You think it's
Yeah,
reliable? Okay, and also I would like to talk about why the refraction index changes with the thickness of the soap film. So that was one thing that I wasn't really clear about.
So in this research, we define
Yes.
the thickness of soap film as the thickness of water.
Yes.
So if the soap film is thicker, the density of the thickness of water layer will be larger. So
Yes.
the density of the surfactants will be smaller. So
The density of the surfactants will
will be smaller, yes.
Okay.
And if the thickness is larger, the refractive index will be near to the refractive index of water, which is
Yes.
1.52.
Okay,
so
so
it will increase the
yes,
refractive index.
so I would just like to clear a few things up for why I asked my question, because on your next slide, it seems as if both of these things are water, and so it just confused me at first because I couldn't really understand why the refractive index of water actually changed, because I thought that these two were also supposed to make water. So that was a mistake on my part, so I thank you for clearing that up. However, I would like to add on another question, like how exactly, did you actually measure the density of like these surfactants in the
No, I
water?
didn't measure.
So you
I
didn't
don't
actually measure the density of the soap film,
No.
but you assumed that it would be higher in places where the thickness was smaller and thinner. Okay, I see. And also, I would like to talk about how you measure the minimum angle of the minimum angle Sorry. Yes, the angle you observe. Because the light film is rapidly changing,
Yes.
right? So how exactly did you get a maximum angle or a minimum angle?
So I take videos to
Yes.
to the whiskers and
Yes.
I take the photos of
Yes.
in the videos like if it's
So you analyzed every different photo in the video to find the one which it had the maximum.
No. Every in every photo I measure the maximum branching angle
Yes.
and because it's not
It's
every
not
photo-
fixed, right? Yeah, I know.
It's not. I didn't take the branching angle and I take the maximum branching angle. I just like in one picture it may have a lot of branches
Yes.
and it will have one maximum angle. So
Yes.
I measure the maximum angle here.
Yes, but of course you see because the light film is rapidly changing. For example, here the maximum angle would definitely be this one, but in this photo the maximum angle might be this one.
So I will have a lot of photos in one video.
So yeah, but you had a lot of photos. So I mean, how exactly did you choose the maximum angle? Did you analyze each photo, each
Yes,
frame?
analyze
Each frame.
frame, yes.
Okay. And so of course, so you will have a maximum angle for your thing. So can you tell me, just give me a rough estimate. Where usually do the light whiskers land on the angle? Do most of them appear close to the maximum angle, or do most of them appear really close to like the angle should be almost zero? Just give me like a sort of a guess. Like how is the light whiskers shaped?
So it depends on the different concentration and temperature.
Yes, I understand. But like for example, here we see that most of in this photo at least we see that most of the light whiskers are here, where the angle is not close to the maximum angle, and only a few whiskers are here, where the angle is actually close to the maximum. So I wanted to know but on this side here, you see a lot of the whiskers are close to the angle where the angle is maximum. So I want to know that in your experiments, did you consider that like the patterns that the whiskers actually form, or did you only consider individual whiskers?
I just consider individual whiskers.
Okay.
I don't know why.
Okay, thank you. Okay, I think that will be all for my questioning. Thank you. Okay. So I would like to summarize the points to be discussed. So I think we just to reiterate, I think we had a wonderful discussion with the reporter. So first off, most of my questions I think she provided really good answers to, especially on how they measured the thickness of the soap film and the refraction index changing with the thickness. So first off, I would like to reiterate, I also agree with them that I think they could trust their Python package in measuring the thickness of the soap film, because I think that it would be accurate to the most part because it actually fits the experimental data. And also the reflection index caused by the changes of thickness in the soap film. Although they didn't actually measure the density of the surfactants, I think that their theory can be it's relatively easy to be believed. So I would like to say that in the end, we realized that the reporter didn't actually measure the patterns of the light whiskers. She only talked about individuals. So we think that to better understand the patterns that the light whiskers would make, it would also be important to consider how many light are branching in wider angles and how many lights are branching in closer angles. So we think that might be important, and we can look at that further.
So now the reviewer asks a question to the reporter and opponent.
Okay, so first for the reporter, I'm curious about did you control the environmental conditions, like the temperature, since temperature was also one of the factors that you considered in your experiment. So did you control other factors like the room temperature, the humidity, or other?
Yes, it's about 25 degrees Celsius.
Okay, yeah, thank you. And also, did you consider since in the question it stated that it needs a very small angle, did you consider the incident angle, and is there a threshold of when this kind of phenomenon will happen? Like how small does the angle has to be, or is there a correlation between other factors like concentrations or?
I think the reason it drives the small angle is only because if you don't have a small angle, there's no refraction happen. So yes, small angle causes the phenomenon.
Okay, next. So you said that you heated the heating plate to 150 degrees Celsius. So I'm curious, with such a high temperature, within the soap film be kind of unstable, and it kind of
Yes.
so it would probably disappear.
Yes, it will break easily.
It will break easily. So did you control like other factors, because concentration was one of the things that you measured.
Yes.
So how do you know that when you are conducting this experiment, like during this short duration, the concentration is the same? Because I would assume that with such a high temperature, like the concentration might also change in like.
No, I just add water, detergent, and glycerin for. It's at this concentration, but I don't know why it will change if it's.
You consider quite a few factors in your experiment, and is there like a main reason that you think is most determinant to this experiment? Like, which factor is most important for it to show this kind of
concentration causes the difference of thickness, and the shape for a soap film from top to bottom is also causes a difference of thickness. So I think the thickness is the most important thing.
So you also mentioned like in your experiment conduct you use your hand to move like the soap film in order for it to like form the whisker, right?
The soap film is based on a tripod.
Oh, okay. Then that's my misunderstanding. Okay, so also like your theory is on like the vertical plane, right? Like the light refracts in the vertical dimension. Is that correct?
I don't really understand your question.
Oh, okay. So yeah, I'm going to skip to the next question. And so both of you mentioned like the thickness of the laser, and how do you guys think that it affects the phenomenon? So maybe starting from the opponent, how do you think the light?
Okay, so moving to the next stage, preparation of the reviewer. Okay, the reviewer takes the floor.
Okay, honorable juries and fellow competitors, this is the reviewer from Team Miracle, and today I'll be reviewing this question, light whisker. So my focus on this problem would be like, why do you need a small angle in order for this phenomenon to happen? And why does the laser actually branch out instead of, if it's a simple refraction, why doesn't it just have one whisker instead of branching out? So for the reporter in the phenomenon, there was a very clear video of the phenomenon, and for their theory, they explained with the thickness of water layer and the refraction index and other factors. And for the experiment, they did the concentration of film, so film, the temperature and wavelength, which all are like quite interesting properties of the light in this experiment. And for the pros, they have very clear pictures and videos and photos of their experiment setup and their experiment results. And they consider quite a few factors. However, there is only a very qualitative explanation, and there wasn't a clear explanation for why the results of their observation actually happens. For example, like why does wavelength and other things actually affect these results. And there was no error bar, so I assumed that there was maybe just one or two times of experiment without like too many times of confirmation. So for the opponent, in their presentation, they summarized the structure of the reporter's report, and the pros were that there was a very clear outline of the presentation, and the structure was very complete. And then in their discussion, they also had a very conclusive discussion on a lot of key points that the reviewer is also very curious about. So for the discussion, first the opponent asked like the usage of soap film and how it was heated to 150 degrees Celsius. So the reporter replies that it is just the heating plate, the temperature of the heating plate. However, the reviewer believes that this might cause the experiment condition to vary between experiments. Like if you only control the heat plate, then maybe each time the soap film has a different temperature, and then the concentration, other factors might also be changed between different experiments. And for the measurement of the thickness of the soap film, the reporter said that they shot the soap film and then used Python to analyze it. So there are some concerns that the reviewer has. So first, they should consider the accuracy of this program and whether, since it is an optic like analyze, there should be a consideration of the optic issues of photo shooting. Are there any like incorrect optic stuff in the photo? And next, for the refraction index of the soap film, the reporter says it's mainly on the thickness and density, and the reviewer believes that there should be a verification of the theory and compare it with the experiment, since what the reviewer saw was only a theory. So also they talked about the angle of measurement. And where the opponent last mentioned about like where the light whisker is compared to the maximum angle, and so the reviewer believes that this is a very important and interesting factor that we can investigate. So since this is quite a difficult problem, there are not too many points that they missed. So first, they might consider the effective thickness of the light laser beam, and also the angle boundary for this to happen. And also the soap film probability through time, since it breaks in a very short duration. So what does the probability through time change? And also some other interesting points like the pivot points, the distance from the coincidence incidence to the first pivot point, and maybe like the reason of large angle refraction and why there are many branches instead of just one.
Thank you. So now concluding remarks of the reporter.
First of all, the opponent asked whether I wanted to hear the theory of the phenomenon, and I say I only have the quantitative theory for the physical interference. And he also asked, do you measure the maximum angle in different conditions? And yes, I measure the maximum angle. And what materials that I added into the soap film? And I added glycerin, water, and detergent. And he also asked that I try to change the different wavelengths for laser beam, and I only tried red and green laser beam because I can only buy these two kinds of colors. And he also asked how did the soap film get to 150 degrees Celsius, and this temperature is the temperature of the heating plate. And what is the method I used to analyze the image? And the RGB photos I didn't apply in this report because I think it's not the most important part, because the main focus is on the Lagrange light, not the thickness, the thin film interference, and analyzing the thickness. So, but I still applied the RGB value by using imaging. And I measure the minimum angle. I just measure the maximum angle of each branch light. And what is the range of the maximum angle? And I think it depends on the concentration, the rate, the shape, and the temperature. And how is the angle of the branches distributed? Are they mostly distributed near the maximum angle? I didn't analyze the shape. I just analyzed the maximum angle of each photo. And I think the error bar is not, to reply the opponent, I think error bar is not needed because I'm just doing quantitative experiments. Thank you for this.
Okay, thank you. Now the questions from the jury. questions? Okay, so I have one question for the reviewer. You point out the reporter didn't consider the thickness of the laser beam.
No, I meant like they consider it, but then I was curious about like what effect it is gonna have in this experiment.
Okay, so could you say a little more about the thickness of the laser beam?
Actually, I don't know how the thickness of laser beam will affect the phenomenon. Just the thickness, I don't really understand this.
Okay. Thank you. Any questions? Okay, I have a question for the opponents. You also asked the reporter one question about the polarization of the laser beam.
Yes.
So I'm wondering if you use the different polarization of the laser beam in your experiment.
So we didn't actually use different polarizations of the laser beam, but from the several research papers that we've read, it seems as if when the polarization is at some sort of a vertical with like the soap film, it will have a better, it will be easier to conduct the experiment. At least that's what we read, but I don't actually really understand this phenomenon that well about the polarization. We just wanted to ask to see if they actually considered it.
Okay, thank you. So Professor Zhen Xian.
You measure the thickness of the soap film, but do you know the reference index of refraction of the film?
No, I didn't measure the index.
But when we measure the thickness, usually we consider both the thickness and the value of index of refraction. So how do you know only the thickness but do not consider the value of
Because in my theory, I mentioned that a thicker soap film will have larger refractive index.
But in your case, you have to consider the change of index of refraction for very thin film, right? So I think the key point seems to be index of the refraction change.
So you mean I can do some experiments if I change the thickness of, if I change the concentration of soap film, maybe I can do some experiments to see if the refractive index changes.
So I really want to ask all of you, could you try to have a setup determine how to get the index of refraction? Could you suggest a method to do that?
Design the experiment to determine the reflect index of the soap film.
Yeah, that means effective thickness.
So which one wants to answer the question?
So one thought would be like shining a light onto the soap film, and then there would be like different colors showing out, and then maybe we could like see like the different colors and how it converts to other like converts to the refraction of the index.
In their case, they also do that, but they only got the thickness. Okay, that's
By using Snell's law, we can solve this problem. For example, I can
Just a simple answer.
for example, I can have a layer of the water plus detergent, and I can have the incident light with a certain angle, and if I calculate the angle after refraction, and I can use Snell's law to calculate the refractive index of the water and detergent.
yeah, but the film is very thin, and you cannot see the refraction angle, I think, because when they pass through the zero angle. Do you have any idea?
Opponent, any idea to?
So we suggest that perhaps instead of using small angles, we could instead shine the light at a wide angle and look at how it reflects, or maybe the angle for total reflection or something like that, or even diffraction to measure.
Okay, I see.
Okay, thank you. So the jury grading. The score for the reporter 7666766. Okay. The score for the opponent 7788888. The score for the reviewer 7786777. Okay, so thank you everyone. So we will take 10 minutes break. I'll give a presentation on the problem number 2. So preparation of the reporter, and each team write down the representative name on the blackboard.
今天的空白画面。有。刚才为什么没有光？
Okay, the reporter will give a presentation.
Okay, hello everyone. The topic I'm going to present today is problem number 2, circular magnets. And then the problem statement is about a button magnets with different diameters are attached to each end of a cylindrical battery. When placed on an aluminum foil, the object starts to circle, and he wants us to investigate how the motion depends on the relevant parameters. And this is my outline. We'll talk about theory and then the conclusion. And we can look at this graph first. For the left-hand side, it's a smaller diameter magnet, and the right-hand side is a larger diameter magnet. And then first, we want to know the electromagnetic force and the torque. And for the current, we know it is placing on an aluminum foil, so the current will flow from the positive pole and go through the magnets, and then go through the aluminum foil, and then go back to make a current. And so we know the force generated by the magnet 1, which is the smaller one, it's IR1 B1, and B1 is the magnetic field of this small magnet. And in the same reason, the force generated by the second magnet is IR2 B2. And the torque generated by each magnet is 0.5 IR1 squared B2, and same as the second magnet. So we have the net force and net torque, which is the net force is sum of the F1 and F2. We get the total mass times the acceleration, and the net torque will be the sum of the two torque, and then it will equal the moment of inertia times the angular acceleration. But however, if we look at this equation, we can know that if I is a constant, which means the acceleration will be a constant too. So in this situation, the magnet will keep accelerating, but we know that's impossible. So there might be some forces or any reason to cause it to reach some speed that will not let it to keep accelerating. So I want to talk about the eddy's current, which is according to Faraday's law, we know while the magnet is spinning itself, it will generate electromotive force, because the electromotive voltage will be dA over dt, in which we can consider about this little area of the wheel on the magnet. This part is right here, and this right here. So the changing of the area will be 0.5 r squared theta and over dt. So we know the electromotive force, the voltage generated by the eddy current will be this one, which means while the magnet is accelerating, when the angular velocity increases, the eddy's current increases too, and which cause the whole system's current to decrease. So we know there's an equation to describe how the current will be, and it is related to the omega. So we can see if the angular velocity rises, the current will keep decrease, and until a critical point, the current will be balanced, and we'll talk about it later. So this is our conclusion. The magnet will approach the terminal velocity after a long enough period of time, because we just mentioned about the eddy's current, and while the current decreases to a specific amplitude, and then the force will be balanced. So which means the force will equal 0, and then because of the angular velocity, the force will equal to 0, and which causes it reaches a terminal speed. And then while it's going in a circular motion, the centripetal force is generated by the friction force, because there's no any other force available for producing the force. And the third, the force that pushes the battery is the reaction force to the Lorentz force the battery exerts on the floor, which we calculate right here. But at a specific time, the current will decrease until the net force will equal to 0, and it will reach the terminal speed. And that's our presentation. Thank you.
Thank you. The opponent asked the question to the
Oh,
reporter.
so here are some new questions for you. As you can see in your conclusion, you said that the centripetal force is the friction force, but in your theory, I don't see any consideration of the friction force. Can you?
Because we didn't consider about the centripetal force. We only considered about the direction, the force with the parallel direction to the moving direction.
Can you show? I know that it's not on your diagram, but can you show me intuitively how is the friction? Where is the friction?
You mean the centripetal force?
Yes, sir.
Like this, it was pointing here.
Okay. And next, in your theory, you consider that the current is the current does not change as time changes.
We consider about it. Well, it depends on the angular velocity.
And okay, so but does the voltage of the battery changes, and does the resistance of the battery changes?
We didn't consider about the resistance changes.
Okay, and so so you mentioned that there should be a terminal speed.
Yes.
So are you saying that it will not stop?
We don't think. We think it will reach a terminal speed, but by time going on, the batteries maybe its voltage will decrease itself too, but the time must be.
Okay, so you're thinking that it eventually will stop, but it's because the change of the voltage of the battery. Is that correct?
Yes, but we didn't observe it stop.
Okay, that's all.
Okay, preparation of the opponent. Okay, the opponent takes the floor.
Okay, so professors and fellow competitors, I'm the opponent from Team Miracle opposing problem number 2, circuit magnets. So let us first take an overview of the report. So in the entire report, the reporter gives a theory considering the induced EMF, which is the eddy current, and consider a homogeneous magnetic field, and also a current distribution is uniform. So here are the pros and cons. The reporter gives a clear schematic diagram showing that to make us to be sure that what he is talking about. But there are many cons. First, the reporter has conducted no experiments, which we cannot have any data to show what happens in the real world and have a comparison with his theory. And next, there are many contradictions in the reporter's report, such as reporter in conclusion, reporter mentioned about the friction, but in his theory there is no friction seen. And the next thing is that some contradiction. Also, as I asked, reporter believes that the magnet itself does not reach a terminal speed because the voltage decreases. But as I said in his report, we can see no voltage decreasing. And next, so because there is no experiment conducted, I am considering that the theory is unpersuasive because we cannot compare. And so I think that is a important point. Although the reporter does not conduct an experiment, I think the reporter can still give an intuitive explanation for everyone to know how will it fit. But I think the reporter does not fulfill this point. And next, as we said, as we all can see, a reporter has a 4-minute report which has bad time management and a problematic structure of the report which has only a theory and a conclusion. So I prepared some of the points to be discussed, but since the reporter has no experimental data, I think I'll mainly focusing on the theory that the reporter proposed, and I would like to provide some thoughts on the theory and how to improve our knowing of the physics of this phenomenon. So may I invite the reporter, please?
Okay, discussion.
Okay, so first I will want to ask you, can you show me what is the direction of the forces? What forces of the you're considering the Lagrange force causing it to rotate, right?
Yes. Its direction is point. You mean like this one?
No. Can you like show it on your on the backboard? Because we all know that the Lagrange force is on the current is I equal cross B, and can you show that what is the direction of these currents and the magnetic field and the forces?
We look from top to.
Okay, sure.
Okay, and then we like this. Draw the magnetic field or.
Oh, can you like stand here like so around you see? So you're saying that this is the floor, right?
No, we look from top to bottom.
Oh,
Yeah.
okay. So but can you show me like if we look on, so this is the magnet, right? And this is the battery and the magnet. And can you show from this point of view what is the current flow and what is
how does the current flow?
yes, and the magnetic field and what is the force?
Okay.
The direction of the force.
You mean like this is the.
No, sure on this. Like if you're looking at this side of the magnet.
Oh, okay. So maybe like this.
Okay, continue, and magnetic field and the Lorentz force.
Let's consider like this.
Okay, good.
Okay.
Yes.
And then you can point like will generate the force going pointing outward.
And can you like go? Oh, okay.
Just like can draw the.
Okay. I think maybe some of you are not clear about before saying. I would like to phrase it. You're saying that when it is n pointed outwards and s pointed inwards, maybe you can write the magnetic field pointing outwards of the background. Okay.
Yes.
So we know that the force is I dO cross B. So maybe you can have using the right hand rule, we can know that the force is in this direction, correct? In this direction, and rolling in this direction.
Yes.
Yes. And next, you said that the friction also has a contribution to the motion. Can you go
No,
where?
the friction, what I mean is the centrifugal force, but we consider it as it doesn't have a friction right here because we consider it as a pure roller.
Okay, so in my understanding of purring, if this is the flow and this is the angular velocity, do you think that there is no friction here if it is pure roll?
The reaction, the react force or the Lorentz force is the friction force, which generates its pushing forward.
I'm sorry, you're saying I didn't quite get it. Lorentz force is the friction force.
No, the react force from the Lorentz force is the friction.
Okay, so let me demonstrate what I'm thinking. So the friction, as I said, in this diagram, the Lorentz force is pointing in this direction. This is the Lorentz force, and so it creates a torque in this direction, right?
Yeah.
So the magnet turns in this direction. So I think that if it's a pure roll, and I agree it will be a pure roll if the speed is not very fast. Do you think that? Do you agree with me that the friction is in this direction, and also it is a static friction?
Yes.
Okay. So do you think that this friction is the centripetal force?
No. What I mean is centripetal force is we look from the top to the bottom. This is not the diagram like that.
Yes.
The centripetal force is like this.
Okay. So
it's perpendicular.
well, but you just agreed with me that the friction is in this direction.
One is which causes it move forward, but this friction force is which causes goes in a circular motion.
Oh, so you're saying that there instead of only one friction, there are two kinds of friction?
Yes, but we didn't talk about this centripetal force in our presentation.
Well, do you think that it's not like the centripetal force is the friction in this direction and causes because when it's rotating it has a big rotation and it's a this friction like causes a torque with respect to the center of rotation. Do you agree with me that this friction also does?
Does what?
Creates a torque and make it rotates about its center.
Yeah, it pushes the whole battery to move forward.
Okay. And next, I would like to discuss about the properties of battery because I know that the force from the magnet is very important, but I also consider the properties of the battery is also very important. So do you believe that in this closed system, the resistance in this closed system is very slow, and the main contribution of the resistance is only from the internal resistance of the battery.
No, I think it is the whole system.
No, I'm saying that the most of because I believe that for an aluminium foil and the magnets, their resistance is extremely slow and compared to the
yes, battery.
yes, okay. So in this case, I believe that when the magnet's rolling, the current of the entire system is very high, like about I would say like about 2 to 3 amps.
And then.
Okay, so in this situation, many things will happen. First, the energy of the total of the battery will decrease very fast.
Yes, it will generate hot.
Yes, as you said. So this has two results. First, that the voltage will drop quickly. Correct.
We didn't measure, so I'm not.
Well, so like, do you agree with my statement?
I don't know how fast you need. Maybe 10 seconds or.
No. Like in a 10 minutes.
Oh yes, I agree.
Okay. And next, the temperature will increase.
Yes.
In a very fast manner.
Yes, I agree.
Okay. So what do you think that so in your equation, can you show like where you consider the and neon? Yes, here. If you have ever considered making this because first this V is the voltage of the battery.
Yes.
And the R is, as we said, is mainly because of the internal resistance of the battery.
Yes, the whole system.
So my knowledge to a battery is that when temperature increases, the internal resistance of battery decreases because it's electrolytes in it, and so when temperature increases, the energy of the electrolytes increases and thus a lower resistance.
So you mean the resistance might not be a constant, like?
Yes. So what I'm saying is that I'm suggesting you to make your equation more similar to a real world case. Like if you can consider writing the current and the voltage and the resistance as a function of time. And as you said, this is the eddy current, and finally this.
Oh,
Yes.
you mean we need to consider about
Yes.
how the battery changes
Yes.
its characteristic during time.
Yes.
Okay, so we didn't consider about.
Okay, so to make this theory applicable to our real case, have you ever think about any way to measure how does the voltage and the resistance of a battery changes when time increases?
Oh yeah, we have I have an idea, but we didn't do it. We look from the side. We can make a experimental instrument
Yes.
thing, and then we put this is looking from this side, and then we let the battery keep flowing, and then we can put our mirrors right here and measure the voltage.
Okay, so I agree with you. This is quite a good experiment that can be conducted. So if you have a function of the after conducting this experiment, maybe you have a function of your voltage maybe looks like this, and your function of your resistance may also look like this. And do you think that plugging these two factors into your theory might quite explain well that because because you're considering that it is the battery that make there no terminal speed, and if you think that if you consider this in your theory, your problem will be solved.
So my understanding is you mean even though there's no eddy current, by the battery itself, it will reach a terminal speed because of the voltage and the resistance will decrease.
No, I'm saying that you're just saying that it reaches. It seems that it reaches terminal speed, but there is contradiction because the voltage drops and it eventually stops. Correct?
Yes.
Yes. Oh, I'm saying that if you have this taken into consideration, do you think that this solves the problem and there's no contradiction? Because if we plug in the decreasing voltage, we can finally solve that the magnet eventually stops.
You mean if there won't be a terminal speed, it will stop.
Yes. So yes, if you consider the decreasing of the voltage.
If we consider about this, I believe it will stop.
Okay. So we have a agreement on how to prove the. Okay, so I would like to end our discussion.
Okay. The opponent summarized the discussion.
Okay, so we have some great discussions on the theory and some improvements to improve the theory. First, we have a clearer view of how the Lagrange force is acting on the magnet and make it into rho. And next, we have also considered that what friction plays in this. What role the friction plays in this. And we have agreement that in pure rolling friction, the friction has a static friction and causes a torque. And the reporter believes that there is also a friction pointing to the center, but I think that is quite questionable. And next we have considered the voltage and the resistance change in the battery and have some discussion on the property of battery. And the reporter proposed a very good experiment to be conducted, and I agreed. And we have agreement of this property of the magnet of the battery and would improve his theory, and that's all.
Okay, thank you. So now the reviewer asks the question to the reporter and the opponent.
Okay, so the first question I would like to ask about is the terminal speed. So in your theory, you mentioned that the terminal speed is due to, the existence of the terminal speed is due to the eddy current.
Yes, if we didn't consider about the resistance and voltage.
So the opponent, do you agree with?
I'm sorry, can you rephrase it?
Do you agree that the terminal speed is due to the eddy current?
Yes, I do.
Do you agree with it? In fact, I agree with it too. Okay. So, however, but we know the reason now. But however, what would affect the terminal speed value? What are the relevant parameters of the terminal speed?
the parameters, I think all just right on top. Every parameters will affect.
Every parameter. And then I will ask you, which one is the most important parameter?
If you want me to say it right now, I can give you an answer because I didn't know which one is the most important. I believe every parameters will affect.
Okay, thank you. What do you think?
Well, like as you can see, the induced EMF is caused by can be written in this form. So you can see that there are three parameters. First is the rotational speed, and next is the radius, and next is the magnetic field. So as the rotational speed is also dependent on the acceleration, and so I think the most important factor is the radius and the magnetic field.
Alright, thank you. In my opinion, I think that the total current and the magnetic field is the most important parameter. Thank you. And the next part is about the pure rolling. The reporter, did you really observe this phenomenon?
We observed this, not the whole circular motion. We observed a partial circular motion.
Partial? What do you mean?
A part of circular motion, because it didn't go through a whole circle because our voltage of the battery isn't high enough to.
Okay, I see. Anyway, so how did you prove that your circular motion is a pure rolling motion?
We can prove. So we assume that it's a pure roll because it is in a relative low speed.
Okay, I see what's going on. And since that you say that you mentioned that you didn't the voltage of your battery isn't high enough. So what do you think that you could improve to to demonstrate the phenomenon?
I think there are two ways to improve. One is increase the voltage of the battery, and the second is increase the magnetic field of each.
Have you ever considered about the internal resistance of the battery?
You mean consider right here?
Yes, if you just lower the internal resistance, the total current will increase, and so the Lorentz force will become larger, and so the force will become bigger,
Yes,
and the phenomenon could be demonstrated. A good example is the anti-image batteries because they have really low internal resistance, so the phenomenon could be well demonstrated. I think time is up. Thank you.
Thank you. So preparation of the reviewer. Okay, the reviewer takes the floor.
Alright, so greetings to the reporter and the opponents and the jury. This is Team Mount Curie reviewing, and so now the problem that I'm reviewing is the circular magnet. So let's first go through the outline. So in the observation, in their outline only have the theory part, and they discuss the Lorentz force, eddy current, force analysis, torque analysis, and the existence of the terminal speed. Alright, so overall review of the report. So the reporter provides an easy understanding theory. However, there are two less explanations about the phenomenon, and they didn't show the observation video, and they have no experimental results, and they ignore some part when explaining theories, and that might lead to misunderstanding. Sorry. Point the opponent's speech, the pros are that they point out some parts that the report didn't mention in his report. And secondly, they have substantial pros and cons suggested in their when they were taking their floor. And third, they help us understand the reporter's theory more detailing. And fourth, they point out some parameters that the reporter didn't consider. And the cons are that the opponent should provide more of his own opinion. Alright, the clashes. So the first question, the opponent asks, does the current changes during the whole process, and should there be a terminal speed in the experiment? And the reporter answered that it depends on the angular velocity, and because the change of the battery's voltage. And the reporter thinks that the terminal speed. Anyway, sorry. And opponent part. The opponent asks, what is the direction of these parameters? The current flow, the magnetic field, and the Lorentz force. And the reporter has shown those stuffs on the blackboard. And the next part, where's the friction force? And the reporter agreed with the direction of static force that the opponent mentioned. They mentioned that the friction force, that there is the centrifugal friction force, and the force that appears parallel to the direction of the magnet. And the next part, the opponent thinks that maybe the resistance will increase, and so the opponent suggests that the equation should include the equation of voltage and as a function of time, and the equation of the resistance as a function of time. And the reporter agrees with the opponent. And I think that there are many points missed during the discussion. So the first thing I would like to add to the remark is that the discussion didn't mention that the reporter actually forgot to consider the force exerted by the current field. I mean, the currents itself, it will produce a magnetic field too, and the magnetic field will exert force on the magnet. And in fact, in our calculation, the force produced by the current and the force produced by the magnet should cancel each other. And in our opinion, the reason why the magnet will move is that the current, there are two hypotheses in fact. The first is due to friction, and the second one is due to the current inside the aluminum foil. And because they didn't consider this part, so I think that they make some mistakes in this part. And next part is that I forgot, I have no time to ask the opponent that how long would the t need to be for this to exceed 1%, and so that the error would be really significant to be considered. So perhaps we could, the jury could ask some questions about. All right, thank you.
Concluding remarks of the reporter.
Okay, so here's my conclusion. First, the experiments are missing from my report, and therefore we cannot verify the theory. And however, we have theoretical setup as to how voltage and current might be measured. But we didn't do the experiments due to the lack of time. And we think that the centrifugal acceleration is caused by the friction force, because there is no other force available, which I just mentioned, that there must be a centrifugal force which caused the whole motion to goes in the circular motion. And last, we can consider the decrease in the voltage and the resistance of the battery in future investigation, just like the opponent has mentioned, because we think that's a reason may cause it stop. And that's my conclusion. Thank you.
Thank you. So now the questions of the jury. Okay,
You mentioned the Lagrange force. I just want you to answer whether the Lagrange force is a macroscopic force or a microscopic force. Macroscopic means large body, and microscopic means electron, small. What is it?
Anyone want to answer?
Or yes or no? Just to which one is it?
Is Lagrange force microscopy or microscopic?
So when like first calculating the Lagrange force, it is the macroscopic force on the electrons. But if you like integrate it to the whole current is macroscopic.
So it's a microscopic.
Yes.
So
In
now,
fact, I have the same opinion with your point.
so what?
I think the current goes through.
Just
just a microscopic.
just a choice.
Microscope.
Any other questions from the jury? Okay, Professor Zhen Xianze.
Please show your picture of schematic drawing of your battery.
Basic point.
Okay, I have a question for reviewer and opponent. Okay, reviewer say that the key current generated Lagrange force is over here, right?
Yes, that's my opinion.
Opponent, do you agree his opinion?
No, I don't.
So you think the key current generated Lagrange force is
On the
where is that?
On the magnet.
Here.
Yes.
Okay, so reviewer, since the current here generates Lagrange force, and what is the direction of the magnetic field over there?
Well, in fact, that is one hypothesis that we propose. That is the main reason of this motion. But the reason why we think that the current here is not the main reason.
I'm asking you the magnetic
magnetic
field.
force.
What is the direction over
Force.
here?
That
On the foil.
well, on the foil, because the current is distributed I'll just explain that. It's distributed not like so desirably, just a straight line of current. It is so the magnetic field should be by right hand rule it should be like this. But however, because the current is not so desirably only have this the current on the aluminum foil is not so straight. So
Okay,
the magnetic field is
just a
quite.
point, just a point. What's the direction of magnetic and current at this point, the center of the system?
In the center.
Yeah.
In the center, then I think you mean the magnetic field at this spot?
Mm-hmm.
Yeah.
Direction of magnetic field.
Out of the screen.
Out of screen?
That sorry, maybe.
On
You
the
mean by
bottom
the exerted, the magnetic field exerted by the current, right? Right? I'm just trying to confirm the question.
I cannot answer it, but you can tell me your opinion.
I mean, I'm confirming what your question is your question that asking that what the magnetic field at this spot
Yeah. On the aluminum foil.
on the aluminum foil.
Yeah.
Oh, I think that. Oh, I see. Aluminum foil. You mean the magnetic field exerted by every the sum of every magnetic field or the magnetic field produced by the current?
No, not produced by
The
produced
total
by
magnetic
the magnet.
total magnetic field.
Yeah.
Whoa. Oh, because there are two magnets. Right?
For others.
There are two magnets. It's quite.
In my opinion, I think the point right here,
Oh,
because
I know.
the magnetic field will go, because there is both and poles, so I think it will go down.
Yes.
Are you agree?
I get your point. So because they are both unpoled, so the magnetic field is downward, and so the magnetic field will exert a force. The magnetic field will exert a force onto the currents inside the aluminum foil. Yes, and if the Newton's third law of motion is correct, then that the reaction force of that force should be the force that pushes the battery.
Yes.
Yes.
Okay, thank you very much. grading of the jury. Jury grading. Okay, the score for the reporter 2, 4, 3, 4, 5, 4. So the score for the opponent 7, 7, 7, 9, 8. Okay. So wait.
我说你少念一个7。
So wait. Opponent again. Opponent.
9，然后8。
Opponent. Opponent. 7, 7, 7, 9, 8.
你没有念到自己的。
哦，我自己没念。7. Okay. And the score for the reviewer 6, 7, 8, 7, 7, 7. It's okay. It's okay. Okay. So I give the lowest point for the reporter. Say, you did some theory prediction, but unfortunately you don't have enough time to carry out the experiment. Okay, so thank you very much for everyone's participation, and student, please give a big hand to yourself. The whole process is an exhausting process, so I hope you will take a good break this evening. So we close the final round. Thank you.